So sometimes you're given a table of values and you're asked to make a connection, to assume that a relationship between X and Y is one that there is a rule, and you know and you can work out what the rule is. So you get the table of values and then you work backwards to get the actual original rule. So in this case here, I've got a table of data. And the table of data will tell, and the table of data is, so I've got here, I've got X and Y, 1, 2, 3, 4. And my Y values are 1.5, 6, 13.5, and 24. And I'm told that it is either Y equals kx squared or Y equals kx cubed. And my job is to figure out which one makes the most sense. So does this relationship look more like a kx squared or a kx cubed? And the way we do that is, first of all, we start by plotting the points determined by the table. So I might just quickly throw together 1.5, 2, 5, so it's looking pretty curved. Now, that curve could be from an x squared or an x cubed relationship. We don't know. What we need to do is actually plot we need to take our table of values and we need to go, well, okay, well, what about if we do it as x squared or x cubed? And then we have our y values. Now, all of this still using the data that we have above us. 1, 1.5. 2, 3, 4. I have 24, 6. I have 13.5 here. So now what I need to do is I need to go in and I need to fill in these values here. So I've got 1 and 1. 2 squared is 4. And I've got 8. 9 and 27. 16 and 64. Based on this relationship, what do you think it's more likely to be? Is it more likely to be x squared or x cubed? Just looking at those values. Because what we're doing is we're comparing. So this here is the expected x squared values and then the x cubed values. Ideally what we want to do is we want to find which one is y closer to, this one or this one. Are these y values closer to x cubed or x squared? And I think you'll agree with me that when you look at some of these more extreme values all the way over here, they are far and away, further away compared to where they were before. And the way you can sort of prove that, or the way you can make it make more sense, is if we go to our CAS and we'll go into statistics And what we'll do is we'll go into here now. We're bringing back some old stats information here. And then what we're going to do is in list 4, we're going to put 1.5, 6, 13.5, and 24. And then in here, list 1 squared. Invalid syntax. Ah, there we go. And then over here, we're going to put in list 1 cubed. Now, what I'm going to do is I'm going to plot a scatter plot. And I'm going to compare list 1 to list 4. So based on my axes and all sorts of stuff that I started with, that's what I've got. Now, if I go back to my scatter plot, draw a second scatter plot, I'm going to use crosses this time. I'm going to compare list 2 to list 4. And then I'm going to plot a third set of data on there. I'm going to compare list 3 to list 4. I'll go large dot. And what you'll quickly find is that the values that we're trying to work with quickly disappear. So list 3 versus list 4. Trying to figure out where my dots have gone. They mustn't be visible on the thing. I'll change to oh, they're all the way out. That's why, because they're all the way zoomed out. Never mind. So if we zoom out, we're plotting a 64 versus 24. So it's all the way out here. So it doesn't make any sense to actually use. But the best comparison that we have, I don't know. I didn't turn it on, that's why. Oh, I'm having a very smart day today, aren't I? There we go. And you can compare the stretch of these points. And you can see just how mucked up the graph is when you try and stretch them out too far. So when you're plotting the relationships between x versus y, which is in blue, x squared versus y, which is in red, and x cubed versus y, which is the green dots. And which one of those is a more straight line? That's the question that you need to be asked. And if you look at here on the green dots, it's still got a curve to it. But you could conceivably draw a straight line through those red crosses. So that what this is telling me is that the rule fits the form will fit the form y equals kx squared. And what you'd be able to do is then solve and figure out what the actual value of k is from there. So in this case, what we can do is we can go, we know that when x equals 2, y equals 6. 6 equals k times 2 squared. So 6 equals k times 4, divided by 4, and I get k equals 1.5. The temptation might be to use a different point. However, I find that when you're working with things that aren't 1, might get you a more accurate result sometimes. In this case, it doesn't matter, because if I was to pick the points that I was using, if I was using x equals 1, y equals 1.5, I would get 1.5 equals k times 1 squared, k equals 1.5 anyway. So here's the thing, is that we can use our CAS to set this up, to do a lot of this stuff for us using our CAS. And the important thing to remember is that we can still use our statistics function. So what I'm going to do is I'm going to clear all this out. And I'm going to start putting in some data. Now, if I have a table of values and there's a 0, 0 on there, leave the 0, 0 out for the purposes of doing this regression. All right, it might skew things a little bit. So what I can do is I go, well, okay, well, I've got the values 1.2, 1.3, 1.5, 1.8, 2, and 2.2. And I know that the y values are 6.048, 7.6895, 11.8130, 20.4120, 28, and 37.268. So I have a set of values there, and I'm going to plot them, and we get something that looks like this. If you were to connect that in a line, would you say it looks more like a quadratic or a cubic? An x squared or an x cubed graph? Well, luckily for us, we don't need to worry about it, because our CAS will do it for us. So what I do is I go into calc. So when I'm looking at the thing here, I'm going to calc regression. And what I want to do is I want to do a power regression. And it's going to make a comparison. So I'm going to take the X list and the Y list. Hunky dory. And I'm going to hit OK. Oh, hang on. Power regression. And it's giving me the answers 3.5, 0.00046, so 3.5, and B equals 2.9999983. So again, 3. Round them off to whatever makes sense. And if I zoom out, hey presto, it makes sense. So what sort of graph is it actually? Well, so if I do the power regression, it's telling me B is actually 3. So this graph is actually a cubic. Now, the only reason why it's not exact numbers is because we have only a certain number of decimal places. So you have to do some of that thinking yourself. 2.99, a power of 2.99999, it's literally 3. I can still do that. And then you can draw the graph from there. Well, you can see what the graph looks like from there and then reproduce it. So there, and there it is there. So what you might do instead is go in and graph that in yourself. So that's 3.5 times x cubed. And you can see it's got the same shape as the one from the statistics section. All right, so we'll do one more of those just because it's different. It's a different sort of equation. So, the pressure and volume of a fixed mass of gas when the temperature is constant is recorded in the table below. Let's go over here. I like these. This is a good one. So I have that. What I need to do is I need to find a rule that works for what I've got here. So the question says, sketch the graph of P versus 1 on V. So this is a case of an inverse relationship. So what I would need to do is I need to add a third row here, 1 on V. So what is 1 on, so it's 1 on 5, 1 on 10, 1 on 25, 1 on 50, 1 on 100, and then plot that and that together. So this would be your X, this would be your Y. And what you'll find is the shape of the graph will look something like that. It drops off very quickly. But our CAS can also be used to help us with this. So what I'm going to do is go back to statistics. Going to clear out all the things I don't need, and I'm going to start putting in values. So I'm going to put this up here is going to be V 1, 5, 10, 25, 50, and 100, and over here, I'm going to put in P, 100, 20, 10, 4, 2, 1. Again, you got to make sure that this is your VP, that these pairs are kept intact when you put it into your CAS. So now we're going to go calc regression, power regression. Compare list 1 to list 2. We're actually going to compare V to P. And we get these numbers here. So this is telling me that A equals 100, B equals -1. If you guys remember all the way back to statistics, what does an R squared of 1 mean? It means it's a perfect fit. Alright, so that means our model is perfect. So, I have this A value and this B value, so what I would need to do now is take my A and B value and express and write out the full equation. The rule for P versus D. So I would say that P is equal to 100 divided by V. Or P equals 100 times V to the power of -1. Alright, both are acceptable, both mean the same thing. Alright, but our CAS can help us do these quickly. If the question wanted you to sketch P versus 1 on V, which earlier in this question does, what you need to do is you need to use this 1 on V column that you've created here. And instead of putting V here, you're going to put 1 on V here. And then you're going to have V. And what you'll find is when 1 on V is 100, is 1 on 100, it's going to be there. 1 on 50 is going to be there. And you'll find that you have linearized the data. Now, obviously, I'm just elaborating there, but if you were to sit there and to put it together very carefully, which our CAS can also do. So what I'm going to do is in list 3, I'm going to change it to 1 on V. Oh, no. Let's look at this. Sorry, I'm going to go down to here to cal 1 on V. So it's done it for me. And now what I'm going to do is I'm going to plot list 3 versus list 2. List 3 versus P. All right, got to make sure that if you've renamed them, you have to make sure you're using the correct ones. And as you can see there, dot, 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 and dot. They are in a straight line. Because if I was to do a regression, a linear regression between list 3 and P, it comes out as a 1-to-1 relationship. It's a perfect fit. All right.